Okay, so this is our first module, and really we're not going to be talking a lot about the details of Python in this. The purpose of this module is just to give you a little bit of an introduction to computation. So this is really geared towards those of you who have not programmed before. Those of you that have programmed, nearly all of this you'll already have known. But it might give you a little bit of context, some things maybe that you've forgotten. But for the most part, this is aimed at kind of getting you a little bit more um, background into what programming really is all about, how a computer works. And as we proceed through the next series of modules, we're going to start to accelerate and start to look more deeply into Python. For those of you who have a lot of programming experience already, don't let this module make you think that we're only going to be covering very introductory and basic stuff. We will be ramping up, but this course is designed for people with a range of backgrounds. So let's proceed here. What do computers do? Um, the truth is the computers really don't do much. They're very complex machines today, but at their core, they they really do remain fairly simple. Computers can add, subtract, multiply, and divide numbers, and they can remember numbers, and that's essentially it. They can't do much more than that. The reason we perceive computers being able to do all sorts of different things and really amazing things is that we can combine millions and billions and trillions of these instructions, um, and they can execute so fast that it can give the appearance that a computer is doing much, much, much more. All right, so everything that we see a computer do is a combination of billions of very simple instructions. And one of the key things about programming is realizing that you as a programmer have to think about the simple steps that are going to be combined to make the more complex program work. You're the builder of the program. And so it's your job to deconstruct what might appear to be a very complex program to build, to deconstruct that into smaller pieces, smaller and smaller and smaller pieces that eventually boil down to the simple instructions that we can provide to a computer. Now nowadays we don't have to quite get down to the level of add, subtract, multiply, and divide for everything, but it is a very, very important skill. Okay, so what I want to first start with is probably the most fundamental thing of computing, and it's numbers. So computers, electronic computers, obviously are fairly modern, but we've been using computers, we've been using machines to help us count for centuries, and we need to think for a second a little bit about how our numbering system works, so we can understand how a computer numbering system works as well. So as humans, we deal with base 10 numbering system. Base 10 just simply means each digit can be one of 10 different potential values. Right? And so in our system, our 10 numbers are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Those are the 10 single digit values that we can have. And we have a system where the rightmost decimal place is worth 1. And then as we proceed to the left, each one is of increase worth by a power of 10. Right? And so we all know this. This is stuff that you learned in basic elementary school. The second digit's worth 10, the third digit's worth 100, and then the 1,000, and 10,000, 100,000, and a million. Right? So it's increasing by a power of 10. And so, we think about this notion of base 10, and you wonder, well, why? Right? Well, why do we have 10 numbers? Why don't we have 12 numbers? Why don't we have 8 numbers? The truth is, there's no reason we can't. There's no reason you can't base a numbering system off any value. Um, One could kind of make the assumption that probably the base 10 numbering system developed pretty well for us because we've got 10 fingers, right? We can easily show 10 different symbols to each other. So 10 is a pretty convenient number. um, Maybe if we had 8 fingers, we would be all using a base 8 numbering system. Who knows? convenient for us, but it's not convenient for computers. Computers don't have fingers, obviously. Computers have to actually represent symbols, just like we have to. And computers are built of electronic circuitry. So at their very lowest level, computers nothing more but a bunch of transistors, which are on-off switches. They can control the flow of electricity through them. And so I want to highlight that point. They are on-off switches. Right? A computer system or an electrical circuit can either have current flowing through it at a particular location or not. There's no in between. It's a digital device. It's a discrete set of outputs. So instead of 10 states, a computer works instead with 2 states, on or off, and we usually, just for convenience, instead of thinking about it as on and off, we say 0 or 1. But those 0 and 1, they're not the base 10 numbering systems. They're fundamentally a binary number system. 1 corresponds to electricity flowing through a circuit. 0 corresponds to no electricity flowing through the circuit. And so our binary numbering system that a computer uses works exactly the way the base 10 numbering system works. The difference is that it's a base 2. So what does that mean? Well, first of all, it's going to be a heck of a lot less compact because each digit only has 2 symbols. So if we think about, and it's customary to write binary with padded and zeros here, and that actually has to do with the fact that there has to actually be hardware, wires behind each one of these digits. So we sort of think of it as a machine that can't just sort of invent more digits. We would have in here a 4-bit, and a bit is a 1 or a 0, or a 4-digit computing system, right? So we pad everything with zeros. If this was the base 10 numbering system, we would have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then once we hit 9, we would change the rightmost digit to 0 and carry the 1, all right, to represent the next value in the base 10 numbering system, 1, 0 being 10. In a binary system, we only have 2 symbols, so as soon as we hit 1, when we add 1, we have to set the rightmost digit to 0 and carry the 1. This 1 does not represent 10, right? This 1 represents 2, which is a power of 2 increase over the right. This next digit will not be worth 100, it'll be worth twice what this one was, so 4, and then 8, and then 16, and then 32, and 64, and 256, and it keeps going, or 128, and then 256. So each digit in a binary system increases by a power of 2 instead of a power of 10. The result is that we actually have to use a lot more digits pretty quickly. So if we think about how this counts out, right? So we've got 2, 3 with the 1 here. When we carry the 1 over, that 1 will be combined with another 1, so we'll have to carry it over. So this is not 100, it's actually 4, right? Each unit is worth a power of 2. 5, 6, 7, 8, 9. And we can see even at 8, we're out to 4 digits. So our binary numbers representing of 1 and 0 can also be used to form a logic, right? And so we've got our numbering system, but we can also think about on or off as true or false, right? And this is going to come into play a lot as you program. This is one of the few, this is probably the first part of this section here that is actually going to directly impact your programming. Boolean algebra works with true or false values, and there's a set of operations that are defined. Just like plus can take 2 integers, or subtraction can take 2 integers and produce another, Boolean algebra uses the not operator, the and, or an exclusive or, to take 2 inputs and output a different true-false value. All right, so these are just different operators. And then not sort of makes some intuitive sense. Not takes one Boolean value, so A. If you give it 0 or off or false, and you say not A, well then it flips it. All right, it's just the inverse, the output, the result. Think of it almost as like the negative sign on a value. If you take the negative of any value, you're flipping the sign. The next operation is and. And it takes 2 Boolean values, A and B. For the and output, right? So if you think about, 3 plus 4 equals 7, right? Well, now we don't have plus, we don't have addition, we have an and. The values aren't numbers, they're true or false values. So for A and B to be true, it requires both the left-hand side and the right-hand side to be true. For OR, it's A or B needs to be true for the output to be true or to be 1. If A and B are 1, the output's again 1. These are very, very, very common in programming, not and or. You will use them in virtually every program that you ever write. That Boolean logic will control the flow of your instructions that you send to the computer. You'll constantly be testing different conditions to see which one to use. Exclusive OR is not quite as commonly used in programming. Exclusive OR means if either one are true, but not both, the output will be 1. So you can see A or B, but not in the case where both of them are 1. It's worth taking some time and studying these Boolean algebra tables. These are things that within the next couple of days or so you want to have completely committed to memory and make sure that you don't skip a beat with that when I start using them in our programs. So logic, these Boolean operations, why are they so important? Well, we can take a bunch of transistors, 5, 10, 12 transistors, and we can throw them into this little electronic circuit. We can plug them into each other, and we can produce what we call is logic gates. So these are little pieces of hardware that have 2 wires. And in the case of and OR, and NOT's a little different because it only has 1 input, there's literally these boxes that you can plug 2 wires into, and if you send electricity through the 2 wires of an AND gate, you'll get output electricity out of it. If you send electricity through one but not the other, or from neither, you won't get any output. You can also build circuits such that if either one of these wires have electricity flowing through it, you'll get an output here. All right, and the NOT gate will output electrical current if there's nothing flowing in, and obviously there's a power source at some point to make that happen. And if there's electricity flowing in, it will not have any electricity flowing out. All right, so these are the basic building blocks of all digital electronics, this Boolean algebra. So how do we get to arithmetic and numbers? So we know a computer's really good at numbers. How does it actually do that? Well, it represents the values as binary numbers, and it uses Boolean algebra to simulate regular arithmetic. And in fact, it really truly is a simulation. The computer has no concept of what addition is. It has no concept of adding or subtracting. It literally is a series of AND and OR gates arranged such that when the outputs correspond to certain sequences, we get the right out, and when the input corresponds to certain sequences, we get the right output. So I've got sort of this black box, a 1-bit full adder, and I'll show you the logic behind this in a couple of minutes. But it has 3 inputs. All right? It has A and B, which is 1 bit. All right? So it can either be 1 or 0, this A and B. All right? You think about this 1-bit full adder as being able to add 1 digit of a number together. It also has a carry in, which would be the digit to the right-hand side of this adder, whatever output was coming out of that, the carry. So if we look at this, if A and B and 0, this 1-bit adder will output 0 to S, its sum. 0 plus 0 is 0, that should make sense. 0 plus 1, 1 plus 0 are both 1. Right? So the answer will be 1 at S. So electrical current flowing through either one of these will cause electrical current to come out of this. If 1 and 1, if electrical current coming through both of them flow through the system, nothing will come out of S, right? Because the answer is actually 2, 1, 0. Remember, binary 2. So the sum will be 0, and the carry out, C out, will be 1. So electricity will flow through this if both of them are active. So if you think back to the logic gates, right, and the logical operations, we had an AND gate, and if you look at the carry out, you can kind of get a sense that, well, the carry out is probably A and B or something similar to A and B. The sum coming out might very well be an exclusive OR, right? Because we've got 0, 1, 1, 0 causes electricity to come out. And in fact, if we look at the circuit, it's pretty close to that. And I'm not going to go through the details of how this all works out, but if you actually follow the wires through, you imagine electricity going through from A, B, or carry in, you'll actually get the right outputs just purely based on these logic gates. And an electrical engineer or a computer engineer typically will draw them with their symbols rather than something like this, and you would see a diagram like that as an electrical circuit. Right. And so the reason I'm going through this is not something that I want to, you're going to think about all the time when you're programming or anything, but you should have an appreciation of the fact that that basic one-bit arithmetic is done just through plain old circuits, plain old transit. Remember, each one of these gates just has a couple of half a dozen transistors in it. Now that does one bit, but now we can scale up. We can take these one-bit adders and we can chain them together. So up here, I've got a 4-bit adder, right? So it's capable of adding numbers up to 4 digits wide. Remember, binary numbers, so it's not too high of a number. Actually, in 4 digits, we can only hold the numbers 0 through 15, which would correspond to 16 possible values. So up top, I've got what would amount to A and B. 4 being 0, 1, 0, 0, and 6 being 0, 1, 1, 0, right? And so again, we'll kind of practice our binary numbers for a second here. This digit's worth 1, this digit's worth 2, this digit's worth 4, so you got the 4 plus 2 to the 6. Now we know, excuse me, we know that 4 plus 6 is, of course, 10. The binary representation of 10 is 1, 0, 1, 0. Again, this is worth 2, this is worth 4, this is worth 8. So 8 plus 2 is 10. But now let's think about how this will work. All right, so we've got the first digit of both of our numbers wired, and again, this is just hardware, literally wired into the inputs of the first full bit adder. 0 plus 0 is equal to 0. The full bit adder will output 0, and we saw that before. The carry out will be 0 as well. The second digit flows in, 1 flows in, 0 flows in. 0 and 1 will cause the sum to be 1. 0 comes out of the carry bit. 1 comes in, 1 comes in, 0 comes out. Remember, we've got that exclusive OR, but 1 will come out of the carry bit. 0 goes in, 0 goes in. The 1 with the carry will give us 1. So if you go back and you look at the logic of the AND and OR gates and the XOR gates, all put together, they sort of live inside these one full bit adders. You can get a sense on how we can take a 4-bit number and add them together. Timing is important here, of course. The right bit has to happen. The electricity has to flow through the rightmost bit fully before we start to look at the output of the second and the third and the fourth. On a 32-bit computer, you'd have 32 full-bit adders, all chained together to be able to do arithmetic in 32 bits. On a 64-bit machine, you would just have more digits. Right? So it's the same exact concept. We're just adding digits to these processors. So hopefully, and that kind of condensed half a semester's worth of computer engineering in about 20 minutes, but hopefully you have a good enough sense to believe that a computer doesn't really have to be that smart actually to add numbers. It's really just an electronic circuit. And the same thing goes for remembering numbers. So I'm not going to get into all the details of the circuitry of how this works, but there's different circuits that are called flip-flops that can store an on or off state. The circuit requires some auxiliary power, so if you unplug your machine, your memory forgets what was in it, but it can store a charge. All right, so it can remember whether 1 was placed in or 0 placed in. And so if we think back, what can a computer do? It can do arithmetic. And by the way, if we can do addition, we can do subtraction, right? Because we can take a minus b is the same as saying a plus negative b. If we can do addition, we can also do multiplication. And you can also derive division through subtraction. So we can do all these operations just through digital circuitry. The central processing unit is really nothing more than a lot of machinery, right? A lot of circuits, just as we've seen before. So we've got an adder, we've got a multiplier, and modern systems have a lot of complex machinery in here, or circuitry in here, but it's the same underlying principle. A central processing unit also has some basic registers where it will store memory, store values, and it has a controller that will activate different parts of the chip. All right, will activate or cause electricity to flow through different portions of the chip. All right, and this is the ALU for arithmetic and logic unit. So in main memory, in your computer, you've got anywhere between 1 and maybe 8 sticks of main memory. And again, those are very similar to the flip-flops we just talked about before. And at each location in main memory, you can store data or you can store instructions. Our programs will be stored in main memory, and of course our programs will be instructions. Each one of these instructions is represented by a binary number, but they can be decoded. So for instance, 001 might tell you that it's going to be an addition. The 0, 1, and the 1, 0 might tell you to take from register 1 and register 2, and the output might go into register 0. All right, so this encoding of 0, 0, 1, 0, 1, 1, 0, 0, 0 looks like nonsense to us, but from the computer's perspective, it's actually taking some of these digits and decoding them. The controller will use this and make sure that the arithmetic unit is going to be active. And the controller will take these two parts of the binary number and determine which values to pull the operands in, and take this part of the bits to figure out where to put the bits back. So the CPU is basically just going around and around and around, executing one instruction after another. And again, as a programmer, we need to actually write the instructions. The computer is just kind of sitting there spinning and executing these instructions. Okay, so we know where we kind of get a sense that we can do some arithmetic, we can store some things into memory, but how do we actually see the output? How do we interact with the computer? Well, again, it's just come down to numbers. So a screen, a monitor that you go and buy is divided into a big giant grid, and each grid point is a pixel. All right, so the higher the resolution, the more pixels you have, the more pixels that you can choose to color. To output anything, whether it's a shape, whether it's a piece of text, we have to actually write code. Someone's got to write some code to figure out which pixels correspond to the letter I, which pixels correspond to the letter H, and actually assign a color and code a number representing that color and store it in a very special place in memory called the frame buffer. And at that point, some peripherals on your machine, your graphics card, will cause those numbers to be sent out to the monitor in whatever format we need for the monitor. You might have a VGA cable or something like that. And then the monitor takes care of decoding those numbers and emitting the appropriate light. So we see the colors on our screen at the right locations. But you can imagine it's kind of a tedious process, right? I mean, to actually literally go through and figure out, I mean, we have millions of pixels on modern computers, to figure out which individual characters, individual pixels get colored, and encoding each one of those colors. How do we encode colors? Well, again, it's just numbers. So if we were to think about a black and white monitor, we only need 1 bit to represent color. 0s for black, 1s for white. If we wanted to have 8 colors, we could have 3 bits, which would give us 2 to the third or 8 options. This is the standard RGB color scheme. 000 refers to no color or black. The third digit is blue. The second digit is green. The first digit is red. And then we have our combinations. 8-bit color is not really that satisfying, but if we go up to 24 bits, so 24 ones and zeros gives us well over a few million options. All right, and it turns out that after 24 bits, the human eye can't really even detect that many colors. We can't differentiate between more than a million different shades of any different color. So typical computers will use 24 bits to represent colors. It's an arbitrary numbering scheme, right? There's no reason we could have put the blue bit at the beginning, right? It's totally arbitrary, but it's a standard, it's a convention. Input's the same way, text is the same way, whether it's input or output. The keyboard simply maps buttons to numbers. The numbers that are painted on the top of your keyboard for the letter T, for instance, or the letter, letter D, are in no way, shape, or form transmitted back to the computer. There are various encodings for characters. The most common and most familiar one is called the ASCII character set. And the ASCII character set just simply defines characters, and you see them all here in these white columns, and defines which numbers will be used to represent them. So for the computer, the number 100, if you ask it what character that is, it'll know that, okay, that corresponds to the character D. The letter D, or the character D, will never get stored in memory. What gets stored is the value 100. So all of this is extremely low level, right? We're talking about wires and basic addition, basic arithmetic, storing values to particular registers, to particular locations in memory. We're talking about coloring individual pixels, encoding colors into numbers, encoding text into numbers. Um, we need to do this a lot to be able to do interesting things, right? To play games, right? To imagine a computer game, right? How many operations, how many colors need to be assigned to pixels to play a modern video game? And so, you know, we now have, because computers have been getting faster at such a breathtaking rate, we can execute so many of these operations. We can calculate so many different colors per second that we can move from, you know, the 1980s to present day video games, which require us to be able to color so many more pixels and at so much higher of a rate, at so much higher a gradient. Notice things like 8-bit color happening over here. It's not, these colors really aren't exhibiting a lot of variation, right? Here we have all different gradients of colors, right? So a lot more bits are being used. It takes computational horsepower, but it doesn't take anything more than what I've shown you. It doesn't take anything more than simple addition, subtraction, division, multiplication, and assigning pixel values. So the thing is that we do so much today with computers, and our programs contain so many instructions that issuing billions of commands to a computer would be just ridiculous. So we've built, and we've been building for decades, um, languages that are much easier for a human being to understand, read, write, and appreciate than the binary number system. We're not going to write any binary numbers in this class. We're not going to really think about the hardware or circuitry. We're not going to think about registers and that kind of low-level stuff. These programming languages, they're not plain English. They don't read like an essay, but they are much closer to natural language than binary numbers are. And so you, as a programmer, you are definitely going to need to learn the syntax. You're going to need to learn the rules of the language, just like you had to learn to write English. You need to learn to write Python. Um, but make no mistake that programming is still about figuring out what to tell the computer to do, not necessarily how. And a good an analogy here is that, you know, you can teach somebody to write in the English language, but that doesn't make them Shakespeare, right? That doesn't allow them to write a great novel or anything like that. They might know the syntax, the grammar, but you still need to be able to figure out how to write something of high quality. Programming is a lot like that. You'll learn the syntax, and at the beginning, learning the syntax is hard, but just learning the syntax doesn't make you a successful programmer. And you got to keep that in mind, because part of the frustration as to learning to code is that, truth be told, a lot of people tell people that, you know, programming is easy because here's the language and here's the syntax. I don't think that that's true. I think that programming is hard and it's a learned skill, and it's not because you can't learn the syntax. You can learn the syntax, but you have to learn to think like a programmer. And so I'm going to try to push you during this class to do that through a lot of examples. And so I say think like a programmer, and other people will call this computational thinking. Computers can do basic math, but we need to send emails, and we need to draw pictures on a screen, and we need to play a song. Converting these activities into basic discrete steps is computational thinking. And make no mistake about it, it is hard. It is very hard to do. The way you do it is by deconstructing these complicated tasks into basic steps. And it takes planning, and it takes a lot of thinking. What do we need to do to tell the computer to do things? The book, and I'm going to be referring to the book a lot during all of these video modules. Um, the book talks about the difference between declarative and imperative knowledge, and I think it's a really nice distinction. So you could ask somebody, well, what's the square root of x, right? And you know, a basic definition is it's the number y, such that if you multiply y together, if you square y, it's x. Right? And this is considered declarative. It absolutely tells you what the square root of x is, but it's of no use to you if you're actually trying to figure out what the square root of 72 is. right? That's the definition, the practical or the declarative definition of square root. Um, that's not really what you communicate to the computer. Instead, to the computer, you need to tell it how, right? How do you actually come up with and compute this using the steps that you know how to do, which again is basic arithmetic. Imperative knowledge is what you as a programmer need to tell the computer. It's explaining in instructions and basic steps how to get the answer. I like to think of it as sort of trying to teach a 3-year-old or a 4-year-old how to do it. A 3 or 4-year-old might know some really rudimentary tasks, but if you break everything down small enough, they might be able to do something like this, right? They might be take an enormous amount of time, but they might be able to put together a sequence of instructions or put together a sequence of additions or something like that. But you need to do most of the thinking, right? And you as a programmer always need to remember that you're the one doing the thinking. So imperative knowledge is a plan. All right, so here's one for square root. And this is a really old method. It's been around for thousands and thousands of years probably. Um, to find the square root of x, guess a value, g. It can literally be any value. So that's a pretty easy task. In fact, it can be x, right? So we can just start our guess with x. If g times g is close enough to x, and we have to find what close enough means, just stop, you're done. G is the answer. Otherwise, come up with a new guess. And here's this is the real imperative knowledge parts. This formula or this algorithm says set g to be g plus x divided by g over 2. Right? And so how did we get that? Well, you know, that's there's backstory to that. But if you repeat that basic step, and if you repeat that over and over and over, if you repeat step 2 and 3, you'll find the square root. All right. It might take you a while. It might take you a long time as a human being to do this, but luckily, nothing that we've written here is hard for a computer. All right. A computer is really good at multiplying two things together. A computer is going to be really good at figuring out whether x is close enough, as long as you tell it what enough is. A computer is going to be really good at doing arithmetic and division. So as a programmer, once you know how, or you think up, and nobody's asking you to derive the square root formula here, but if you can start to think about individual steps that include only things that a computer can do, now you can program it. All right, and so, you know, just kind of walking, this is Python code, but we're not really going to talk about syntax just yet. But I have an instruction to ask a user for a number. I have an instruction or a set of instructions that initializes some things. So remember I said, well, you can make g equal to x. Well, I made it x over 2. Close enough, I'm going to define as 0.0005. It's got to be within 0.0005 of the answer to be acceptable to me. Here's a little loop that continually resets the guess to the next value as long as it's not close enough. And what we've done is we've taken the absolute value of g times g minus the value that we're trying to find, the square root of, and if it's greater than our threshold, sometimes we call this epsilon, we just keep going. Right? And again, don't worry too much about the syntax. What you should realize though is the breakdown of it, how it's actually flowing. Once I figure out what it is, once I've executed those instructions, I print it out, and I can tell the user the square root of 72 is 8.4852, blah, blah, blah. Right? So again, the Python's not important here. This is Python code, and this will work. You can type this in, you can get the right answer. But what's critical about it is understanding that you've essentially explained to the computer what to do to find the square root in terms that it can understand, in terms of basic arithmetic. So that method is really often called an algorithm. Imperative knowledge represents a series of steps, right? So as a programmer, you need to think of a series of steps ordered, right? Do this, then this, then this. Each individual step will be simple, but put together can do very, very complex things. All right, we have algorithms that can detect images out of, or detect shapes out of images. We have algorithms that can find a similarity between two different songs. But it's all done the same way. We think about very, very simple steps. Programmers often call these series of steps algorithms. maybe because it sounds a little more complicated than imperative knowledge, but when you hear the term algorithm, it really is just a series of steps. Programming is about learning to develop algorithms to solve complex problems, and knowing the syntax, and in this case of Python, so the grammar, the structure, the keywords, so that you can write these algorithms in a way that a computer can understand. Most people think skill number 2 is what's important. Most people, and you will start with skill number 2. That's the first thing that you immediately see, because you have to learn some syntax to be able to write any code. But I can't stress this enough. Number 1, developing algorithms to solve complex problems is the most challenging, and it's by far the most important part. A good programmer can pick up new languages. It doesn't matter what language a good programmer works with. They might struggle a little bit with the syntax in the beginning, but they'll always be able to solve problems because they're good at point number 1. Someone who is not good at point number 1 can learn many, many different programming languages and still will not be an effective programmer. Right? Just like if I can't really tell a good story, it doesn't matter if I learn a new language and tell the story in Spanish. It doesn't help me. It's still a bad story, right? And so you want to focus on number 1 as well. It takes a lot of practice. It is difficult to do. There's no question about that. Anything that's difficult to do will result in errors. Errors are, or we call them a bug. Bugs are a fact of life. Okay, so one of the first things, if you're just programming for the first time, I think it's very likely that you will be frustrated at some point during this class. You'll get frustrated that your programs don't work, right? And it can be frustrating. Keep in mind that everyone makes these errors. All right, it's to be expected. An enormous amount of effort goes into professional software development simply for finding bugs. And so if people are willing to spend all this time trying to search for bugs, you can be sure that they exist, right? Everybody makes them. There are 3 general types of errors. You've got syntax errors, which are analogous to misspelling something or missing a period at the end of a sentence or in an essay. All right, so they're grammatical problems. Syntax errors are actually pretty easy to deal with because when you run the program will stop. The program will tell you this is invalid syntax. So they are frustrating and they take some time to correct, but the bottom line is that you know that they exist when you type them. When you type them, you'll find them. Runtime errors are more analogous to using the wrong word in a sentence, to say that analogy. It's something that's grammatically correct. So I mentioned the word there versus there, right? Different spellings of the same word. The meaning of your statement is wrong, but syntactically it's okay. All right? These are tricky errors because the Python itself probably won't be able to tell you there's something wrong with your program, but your results will be wrong. All right, so if you're being asked to write a program to calculate the square root, and the user says, I want to know the square root of 81, your program comes back with, 7, right? That's a wrong answer, but there was nothing syntactically invalid about your program. All right, so those errors are a little harder to find. You need to make sure that you test your program, and you might find some instructions that you maybe didn't write correctly. The third kind actually are the worst, logical errors. Logical errors are analogous to writing an essay about the wrong topic, right? And I say, because in this case, if you're asked to write an essay on a civil war, and you write an essay on the World War II, you might write a fantastic essay, but you've wasted your time, and it's wrong. It doesn't matter. Right? And so those type of errors, logical mistakes, are going to be a real problem. You're going to make every single one of these. I make all of these. Every programmer on the face of the earth makes all three of these type of problems, errors. Syntax errors will start to fall away quickly. Sometimes you'll make them. You'll have typos. You'll miss that. I make syntax errors all the time just by hitting the wrong key or something like that. Those are easy to find. You'll get better and better at finding those as time goes on. Runtime errors absolutely happen. They're easy to correct once you find them. They generally are easier to correct. They might be hard to find, but they're generally going to be fairly easy to correct. It's the logical errors that you want to stay away from the most. Really good programmers very, very, very rarely make logical errors. The wrong sequence of steps, even if you program them perfectly, are always going to be wrong. The only way that this is not about, typing skills or language skills. You need to make sure that you've thought carefully about the question. Don't write a program for a problem that doesn't exist. All right? You must make sure that you avoid logical bugs. No hand waving. And what I mean by that is, no hoping that sort of everything will just work out. You must actually think through everything that you do as a programmer. So this course, we're learning Python. Python is, and for those of you that have experience in other programming languages, I can tell you that Python has some features that are very, very unique. So even if you're great at C++ and Java or some other language, you're going to get some things out of this course because Python deals with basic fundamentals like variable scope. In just a very different way. Even the way the syntax works might be kind of an eye-opener for you. We will also learn how to create algorithms to solve. I'm going to try to, as we start to accelerate a little bit, we're going to move more into the, solving scientific type problems, really as the topic. But the programming skills that you learn can be applied to anything. We'll learn how to find our bugs. I'm going to have a lot of video of me programming, and I'm going to make a lot of mistakes. Some of them will be on purpose, some of them won't be. And I do that, and I'm not going to edit them out or anything like that because it's really important that you see how I find bugs and how I figure out what the problems are. Really good programmers make lots of mistakes still, but they've gotten very, very good at finding them extremely quickly. And that's a learned skill. That's not something you can read about. It's not something somebody can tell you how to do. This just takes a lot of practice. Don't get frustrated. Every bug that you find, you're getting better at finding bugs. So, how to succeed? First of all, if you've already programmed in another language, if you're a computer science major, the beginning of this class is going to be probably very easy. There's going to be in each module a couple of new things that you're going to learn about Python, so it's definitely worth spending the time looking at all the lectures. But as the semester continues, or as the course continues, you're going to find some of the assignments are going to start to get quite a bit more challenging. So don't get lulled to sleep right in the beginning. If you are new to programming, you're going to find the very beginning of the semester to move probably at a reasonable pace. It's geared towards someone who's not programmed before. But be aware that we're going to speed up. This course covers a lot more material than a typical CS1 course might do. And so you're going to have to stay on top of what you're doing, and you're going to need to make sure that you're up to that you get any confusions worked out, especially along our schedule. The best advice that I can give you if you're new to programming is that you must do the coding yourself. Lots of subjects, you take biology, you take physics or something like that. You can read a book, right? You can look up a book and you can learn the formulas and you can just do it. Somebody can tell you what the answers are. They can tell you about the biology or the anatomy of some animal or something like that. I liken programming much more to playing a sport, playing an instrument. It is something that, yes, you have to learn the fundamentals from an instructor, right? You have to learn the syntax. You have to learn tips from a coach, from a book, right? But if you've ever played a sport and you've ever played a musical instrument, you know that it doesn't matter how many times you watch somebody you know, hit a baseball. You don't get good at it unless you're the one doing it. You can pick up some tips, you can pick up some pointers, you can get good habits from watching people do it, but you don't get good yourself unless you practice a lot and that there's no shortcuts, right? And so that's the big takeaway right now. During the next module, I'm going to start to introduce the syntax of Python. In each one of these modules, or actually the first couple we don't have specific exercises, but after that we'll have programming exercises in almost every single one of these modules. There'll be opportunities for you to code. The more you code, the more you struggle to find your errors, and the longer you spend on this, the better you will be. If you ask me to solve your problems, right away, as soon as anything happens, um, you might get an okay grade on the assignment because I'll help you through it, but you won't learn a lot. And then the next problem, or then on an exam or something like that, you won't do well. If you struggle through the practice exercises, you'll struggle less on the homeworks. And if you struggle less on the homeworks, you'll struggle even less on the exams. Right? So put in the time, and make sure that you do as much of the programming you can yourself.